Hi everybody. In this video we're going to take a look at how to solve an advanced mole calculation problem. So you can see that the problem is right down below me, right here. We want to convert to find how many milligrams of oxygen are present in a sample of carbon dioxide which contains 3.0 times 10 to the 20th molecules of carbon dioxide. Now in order to solve this we're going to use the mole bucket diagram, that's right over there, and we're going to use that to help us diagram a strategy in order to solve this problem. So let's go ahead and take a look at what our strategy is going to be. First step, we are starting with information about how many molecules of carbon dioxide are present in the sample. We want to figure out information about oxygen, so we need to convert from molecules, MC, of carbon dioxide to atoms of oxygen. That'll be step number one. Step number two, we're now talking about that we have a number of particles, atoms. We're going to convert from atoms to moles. So we're calculating to get into the mole bucket. We'll be using Avogadro's number as a conversion factor to do this. So I've diagrammed step number two for you right here. Our next step, now that we're in the mole bucket, will be to calculate out of the mole bucket to determine the mass of the oxygen present in that sample of carbon dioxide. So we want to convert from moles of oxygen, atoms, to grams of oxygen. So step number three is going to be calculating out of the bucket to calculate a mass. We need to use molar mass in order to complete a calculation like this. The final step in our calculation is going to involve converting from grams of oxygen to milligrams of oxygen, because we want to make note that the question is asking us to calculate milligrams of oxygen present in the sample. So let's go ahead and take a look at how we would use dimensional analysis to set up and solve this problem. We're always going to start with our initial measurement. That is the 3.0 times 10 to the 20th molecules of carbon dioxide. I'm sorry that my decimal point didn't show up very well. It should be 3.0 times 10 to the 20th molecules. I'll use MC as the abbreviation there. Molecules of carbon dioxide. We want to convert this to atoms of oxygen. In order to do this, we'll interpret the chemical formula CO2. In every one molecule of CO2, there are two atoms of oxygen present. So we can see that molecules of carbon dioxide would cancel here and here. If this was the only thing that we would do, we would calculate how many atoms of oxygen. We've now completed step number one in our strategy. Our next step involves converting from atoms to moles using Avogadro's number. I've rounded that off so that I could fit it on screen here. Normally I ask my students to use the full value, 6.022 times 10 to the 23rd atoms of oxygen in 1 mole of oxygen. Atoms of oxygen will cancel. We would now have calculated the number of moles of oxygen present in the sample. We're now in the bucket. The next step would be to convert from moles to grams. This is step number three that we're setting up right here. We're using the molar mass of oxygen, which we can find on the periodic table. It's 15.9994, but we're rounding that off to 16.00. We would now know how many grams of oxygen are present in our sample. Our final step will be to convert from grams of oxygen to milligrams of oxygen. So we need to use the relationship that 1 gram is equal to 1,000 milligrams. The final solution of 16 milligrams of oxygen was calculated using the following steps. Molecules of carbon dioxide, 3.0 times 10 to the 20th, was multiplied by 2. That value was divided by Avogadro's number, 6 times 10 to the 23rd. The result there was multiplied by 16, and that result was multiplied by 1,000 to find the final solution. So some important things to remember here. To convert from particles to moles, we're using Avogadro's number in this step. That's step number 2 right here. To convert from moles to mass, we're using the molar mass. For an element, we find that directly on the periodic table. Thanks everybody for watching, and good luck with all of your chemistry problems.